Good morning, everybody. I am Puja Chowdhury. I am working with Dr. Austin Downey, and I am here for my dissertation defense. My dissertation title is Hardware Software Design for Temporal Forecasting in Structural Health Monitoring. My dissertation committee members are Dr. Downey, Dr. Bakers, Dr. Wang, and Dr. Lee. Welcome to my dissertation defense. I will start with the research overview and then I will discuss in detail research area 1 development and research area 2 adding physics. At the end, I will summarize everything in the conclusions. Let's start with the research overview first, which includes the background of structural health monitoring and time series prediction. In case of structural health monitoring, I will discuss about a case study named high rate dynamics. The next is the motivation of this research, which has two questions. First one, how to design hardware and software for real-time forecasting for structural health monitoring. The second one, how to synergize between data-driven and rule-based systems. Next, the relationship of these research questions in detail, key contributions, and publications. Start with the structural health monitoring system background. It is a method of evaluating and monitoring structural health. In the left figure, we can see it's kind of a breach monitoring and evaluation. If we see this breach, if there are some kind of damages, we need to monitor it. And after that, we do the data analysis. From this analysis, we will make a decision. Is it need to alert or we are safe? Something like that. There are lots of type of structural health monitoring need to monitor as like the levy monitoring. For the case study, the important thing is the high rate dynamics. So we need to know what is this high rate dynamics. High rate dynamics are described as a dynamic response from a high rate, which is less than 100 milliseconds, and a high amplitude, which is more than 100 G acceleration. It's some kind of a blast or impact, as like the figure, vehicle collision, ballistic packages, hypersonic vehicles, space launch system, etc. There is also some other subject along with the high rate dynamics, which is like the large uncertainties in external loads. It's kind of the vehicle collision and sudden impact. High levels of non-stationaries and heavy disturbance, like the Space Launch Shuttle system. Also, there are some unmodeled dynamics from changes in system configuration. Now talk about the time series prediction, which is also an important part of this dissertation. A time series is a set of observation if we consider y a quantitative variables collected over time t, that is the time series. In time series analysis, we analyze the past behavior of a variable in order to predict its future behavior. There are some components of the time series prediction or time series. If we see the picture, the first component is the trend, which is a long-term trend. It could be growth, it could be decline or constant. Here it's kind of a growth. Next is the seasonal behavior, which is like the upward and downward movement repeated at the time over the year. With the something similar like the seasonal variation, there is another component like the cyclical variation we can see over the time series. Finally, there is a irregular fluctuation or random effects, what we can see or say as like a noise. If we consider all of these components, there are two types of time series model. If we add all of these components, that is called additive model. If we multiply all of these components, that is multiplicative model. For time series prediction, there are several approaches in research community as like statistical model. Some example of this model is the ARIMA, SARIMA, and LASSO. In machine learning model, ANN, decision tree, and gradient boosting are some of these examples. In case of deep learning model, mostly renowned models are MLP, CNN, and RNN. Recently, a huge interest have been developed for physics-informed machine learning model. Mainly here are six types of physics-informed model as like physics-constrained machine learning, data augmentation, transfer learning, two types of data learning. First one is the missing physics, second one is the machine learning prediction, and sixth one is the machine learning assisted prediction. So this is the overall scenario of time series prediction classification. As I discussed high rate dynamics and time series prediction, now my goal is to temporal forecasting in the high rate dynamic system. In application, we need real-time decision making of the structure. What required technologies of low latency model development, updating system state prognostics in real time. Let's see a high rate effect. In this video, it's kind of a drop tower impact. So this how we can explain what is the challenges of high rate dynamics. From this video of the drop tower, we can see there are some unknown sources. The first challenge is not that. The first challenge is the computational power is limited, the memory, energy, and processor. Second one, the unknown source of the input, force location, just like the drop tower sudden impact, and also inavailability to calculate false scenarios in advance. And this is also rare. It happens in extreme situation. So considering these goals and challenges, here comes our research question 1. How to design hardware and software for real-time forecasting for structural health monitoring in case of high rate dynamics. And here the research question 1 comes with some subsequent goals. First one, data generation in experimental environment. Next, model development for temporal forecasting, and finally, hardware implementation in FPGA. Here is a simple layout of this first research question we can see. The contribution of this part using a co-design approaches. That's why here we consider this part hardware software design or co-design. Developing some faster system. Here I develop FFT and MLP approaches and do the real-time implementation in FPGA. But it comes with some cons too. The first cons, it's only use the data-driven approaches. Here it still have the memory problems, computational problems. So we need to deep down more. To solve the cons of the research area 1, we need to know what is the data-driven approach. So in case of data-driven approach, here are the data. So based on the data, there are some evidence. So we play in the hypothesis space after that, and from there, we make the decisions. But in case of rule-based, there is no data. So there is already some hypothesis. Based on the hypothesis, make the decision. Both approaches have advantages and also disadvantages. For the data-driven, the advantages are self-learning system, handling more complex problems, performing better with less human interaction than rule-based system, adapting over time via continuous learning to changes in data and environment. What are the demerits? Needs to see a large number of input because it's a data-driven process. It's use only the data, not intelligence in the sense that humans are. In case of rule-based, the advantages are easy to understand and interpret, quick implementation, easy modification, durable in nature, compatible with machine learning and AI. But there are also some disadvantages, like the problem with vast number of variables, with so many constraints and limited intelligence. As we see, data-driven has some good points and also some demerits points. Rule-based follow the same type of pattern. So how can we find out some common ground? Here, our research question 2 came. How to synergize between data-driven and rule-based system. That's how we find out maybe physics information learning will be a good approach, which will be a middle ground between these two approaches. Now, start with the integrating physics information learning for structural health monitoring, which also have some goals. Is start with the data generation in the experimental environment as like the research area 1, but here is the additional thing, physics data generation via finite element model, and then model development for temporal forecasting. Here is a simple layout of this overall physics informed part. What are the contribution? The contribution actually start with 2 models. The first model is like the integrating physics data. The second one is the transfer learning to reduce data dependency. So both cases, we made two problem-specified custom model named PISP and Pimento in here. And also the good point, this solution solves all the cons of the research area 1. Now here, as research area 2 solves the cons of research area 1, so we need to know how the combination of data-driven and rule-based model works actually. So these slides actually show the transition between data-driven to the machine learning or physics-informed machine learning. So the blue actually considered the data-driven approaches and the yellow is considered a physics-informed machine learning part. So in the beginning, if we considered here, there is no physics, only the big data that considered as a purely data-driven. And gradually, when we put more physics, less data, it's moving to the physics-informed machine learning approaches. That's how we found out the middle ground of physics-informed machine learning for our research question 2. Let's look at a preliminary layout of the relationship of my research. The first research question comes with the how to design hardware software for structural health monitoring. We designed, we made data, but we have some cons. To solve that cons, we have the other research question 2 coming out, how to synergize between data-driven and rule-based system. These two research questions combine my overall final dissertation, hardware software design for temporal forecasting in structural health monitoring. Now, a detailed overview of this dissertation starts with research question 1, how to design. So I designed two models, FFT-based time series prediction and MLP-based time series prediction. For this part, also generated the data from experimental setup, made the software development in the model, also implemented in the hardware in FPGA. But this overall part is based on data-driven machine learning. So we want to remove that cons of this part, also improve the model more. That's how the second research question coming out, how to add physics. So in case of adding physics, I developed two models. Also for physics data, made a FEA model. Here are two approaches or two models from the physics information learning. First one, we can say that physics data enhance or data augmented time series prediction. Second one is like the physics knowledge transfer based time series prediction. So these data driven and physics information learning combined and make the final dissertation hardware software design for temporal forecasting in structural health monitoring. Here are the key contributions of this overall dissertation. What are these? So first is the data generation. Here are also, I mentioned which area covered what is the contribution, like the research area 1, 2, and etc. So in case of data generation, research area 1 and 2 both make experimental data generation. Why we need to do that? Develop solution to overcome the lack of available data for high-rate dynamic system research. In case of research area 2, here is the addition of physics-informed data. So we utilize the physics principle to generate realistic data for high-rate dynamic system. Next approach is the data-driven model development. In case of research area 1, direction 1, make a mathematical algorithm-based model, FFT fashion, window fashion model. In case of research area 1, the direction 2 follows a deep learning-based model, which is the ensemble MLPs. It's created and gave some good performance. For improving the model and remove the cons from previous analysis, I do some physics-informed model development in research area 2. Research area 2, there are two directions. First direction, I followed the data augmentation, which built a problem-specific customized model named PISP. And the second direction followed the transfer learning-based machine learning, which is another customized model named Pimento developed and gave some good performance. I didn't only stop to doing the software implementation. I did hardware implementation in case of research area 1. For both direction, I did time deterministic hardware implementation in FPGA for both model FFT and MLP. So what are the application? Here in the dissertation, the application is in the high rate dynamic system. We tried with non-stationary time series prediction and gave some good accurate prediction over the time, and also tried with the single impact prediction, which is also successfully predict the impact over the time. Beyond my dissertation, I also work with other project named Data-Driven Fragility Framework, which has developed a framework for risk assessment of levee bridge. Now let's look in the publication. As I have two research questions, there are also two parts as well, the design part and the improvement part. In case of design part, in research area 1 and direction 1, I have the publication for FFT software at around 2021. The research area 1, in the direction 1 for FFT hardware, there is another published paper. And in case of MLP, the direction 2 for research area 1, there are two papers. And for this same direction, I have a future plan, which is still in the development stage. It's like a comparison between these two approaches in hardware and software. After that, for more improvement, I do the research area 2, start with the physics informed review. Here, I have two workshop paper in 2024. At the same time, for this area, I have first direction, which belongs to a data augmentation process, which is in the submission stage, and the next approach, which is based on the transfer learning based physics informed machine learning, which is also in the submission stage. So beyond this dissertation, I also work with the other research project, risk assessment of levee bridge, where I have 6 papers. So if we see the summary of this overall publication, I have 10 published paper, 1 submitted paper, 3 in submission stage paper, and 1 in the development stage paper. That's how I'm done with my overall research overview. Now start with the research area 1, hardware software development. So it starts with the experimental setup for data generation. So here is the beam structure of the system. Then start with the control computer, which sends the pre-developed or generated excitation signal through the power amplifier to the shaker to excite the beam. After excitation, we measure all of this information through the accelerometer, and finally, all the data is collected through the data acquisition module. We also use a load cell to measure the force of this system. All of this generated data is available in a public repository in GitHub. Here's the link. As we talk about how we do the experiment to create the data, now little bit overview how actually we made the excitation signal, the non-stationary type of signal, one type of simple explanation here. So if we consider the first half of this signal based on 50, 70, or 100 frequency, second half 50 or 100. So we concatenate these two sine waves around 5 seconds to make this non-stationary effect. So that's how a non-stationary is presented due to a change in the frequency. We can see this data, the right side data, there is a small changes, but here in the middle around 5 seconds, there is a sudden impact which is created by the change of frequency. But we generated this type of several data, which already available in the GitHub, I said. But for this explanation, we use this data and also make 4 other different sample data. So now research area 1, start with the first approach, software implementation approach, FFT based prediction. How this prediction works, if we look at the right side, that is the left side, here is the flow chart. So if we see, it starts with the input data. Here we mentioned is at a learning window length, which is L. Then it's passed to the trend. We need to find the trend and need to remove it from the input data. Next step going to the FFT. After FFT, we measured frequency, amplitude, and phase. After this, we collect specific numbers of frequency, which has more impact on the data. Then next step is the extended time scale. How much we want to predict, that much we want to extend that. And next step, we need to add the trend, what we removed at the beginning of this algorithm. And that's how the overall FFT-based prediction is working. So here we can see this is the learning window. The input is L, the prediction is P. If we look at the right side animation figure, we can see the middle is the FFT-based prediction model. The left side is the acceleration signal input, and the right side is the orange one, the prediction signals. And in between that, we can consider the model is running through a computational time, which we consider as a capital T. The overall process is running over a rolling window approach. That's how the FFT is working. For analyzing the result of this approach, I considered three different stages over the data. Here we just explain for one single data when we consider learning window 0.5 seconds. So the first event is the pre-event steady state. The next event is the transient event. What is the transient event? It is the event, it's the transition between non-stationary to the stationary to the non-stationary. Then after this event, we consider that event as post-event steady state. So in case of pre-event, like before that non-stationary happens, the prediction is much better. Even after that, the post-event state, it is better. But in case of passing this transient event, the prediction is little bit fluctuating. From this software analysis, we make two types of hypotheses or two types of effect analysis. First, the learning window effect. So in case of learning window effect, we can see in these two figure too, error and learning window have a reciprocal or inversely relationship here. In this first figure, we can see even in these three events, in all cases, if the error is going down, window is going up. It's like the inversely related here. So we tried with 0.1, 0.5, and once again, learning window. In case of transient time, if we consider the relationship window, learning window, it's proportionally related. What is transient time? How much time it will take to pass that transient event. So when the learning window is smaller, around 0.1, then we get the lowest transient time, around 0.4. So when it is high, the transient time is also high, as like here, for 1 second, it's 1.2. Another analysis, we consider the computational time effect. So in case of computational time effect, the error and the transient time both has proportional relationship with the computational time. So the left figure, even we can see for three of these events, pre-event, transient, and post, in all cases, if we increase the error, its mean computational time is high. If it's decreased, its mean computational time is decreasing too. In case of transient time, it's same. When there is more error, it's mean it's take more computational time. Now, start with the direction 2, which is the ensemble MLP in software. So here is a flowchart of that ensemble MLPs. It's again start with the measured signals like the acceleration. As it is an ensemble MLPs, we use 3 MLPs here. So there are 3 inputs, T1, T2, and T3. From passing the MLPs, there are 3 hidden representation coming out, H1, H2, and H3, going to the attention layer, find out another output A, which is passing to the linear regression, and then get the forecast signal. But in here, we do the back propagation through the attention layer, tune the weight and bias in the attention layer, linear regression part, and make the calculation, and then make the final forecast signal. That's how this ensemble MLP works. Now coming to the result section. Here, we consider two sides of the data. First, before non-stationary, and the second, after non-stationary. From the plot, we can see separately before non-stationary, what is the changes, and after, what is happening. But it will be better to look at the numeric values. We can see here before non-stationary, RMSE, SNR, and convergence is pretty good compared to after non-stationary events. Even in the picture, we can see in the figure, the B figure and C, we can see after non-stationary event, it is peak high and gradually going down. But compared to before that event, it's lower. After software implementation, I did hardware implementation in FPGA for both FFT and MLP. Here, I use the Serial 9035 Intex 7 FPGA for hardware implementation. Here are some steps of this hardware implementation. Normally, we use LabVIEW FPGA for this implementation, which is a module for designing and translating them directly to hardware. After this, next step is the Xlinux Vivado, which is a compilation tool. After that, if we run, it's saved into a bit file generation, and it's end up with the hardware implementation. Now talk about the hardware validation part in case of FFT. This FFT flowchart, we can see here how it's work. It starts with the acceleration signal. It's almost same like the software implementation, but we now use the hardware terminology too. Next is the signal conditioner, and then we use a ADC, the analog to digital converter. And next step is the FFT process, collect specific frequency, restore signals. But inside the FFT process, there are some steps like we need to do first FFT, then real value measurement, imaginary value measurement, then we do the measured phase and amplitude. And finally, we get from the restore signal a prediction of 1 millisecond into future. So this is the overall hardware process happening inside the FPGA. But in the hardware implementation, here are some size limitation of built-in LabVIEW FPGA FFT function. It's limited to 8 to 8,192 samples. For each of these FFT size, there is a latency cycle from 16 to 16,384. So we consider this analysis, this different sample rate for the hardware implementation part. These are the samples like 25,512 and 256, 128. For each of the sample rate, I use this FFT combination, and this is the input sample. For 25,000, I cannot use the 25,000 FFT size due to the size limitation of the LabVIEW FPGA. Now look at the simulation results for this purpose. So in case of simulation results, we can see for the highest sample rate, even in the table, we can see when 25,000, the SNR and RMS is pretty good. And in case of the lowest sample rate, 128, this performance is worse, even in the numerical number, even in the bar plot. But what is happening in the hardware? That is the main focus of this hardware implementation. So in case of hardware implementation, it's a little bit different. In here, the 512 sample rate takes greater computational time than other sampling rate. It has the largest computational time we can see here. And in case of the computational time, we separated different steps of this overall algorithm, like the data input, FFT process, collect a specific frequency. So that's how we measure the computational time. In case of device utilization, the right plot, we can also see for 512 sample rate, it utilized around 96% of the FPGA slices. So in here, in the hardware implementation, we can see that 512 is performed pretty well. But why 25,000 doesn't work perfectly? Because it requires its pairing with reduced FFT size because of the size limitation to enable its deployment on the chosen FPGA hardware. Now, here are the hardware validation of MLP. So this is the flowchart of the hardware implementation in case of MLP, how it's work. Again, we start with the signal input acceleration. Next is the DAC. The sample rate is around 25,000 sample per second. We use a register which feed 50 samples per cycle. The next step is also separated in different with different steps: data in, subsampling, data manipulation, MLP forward pass, then attention layer and back propagation. Finally, we reach the prediction of 1 millisecond in future. So in the table, we can see how much device utilization is happened in FPGA. So it's around 96.5 thousand for the device utilization. But for the time requirement for the different specs, we can see here for the total system, latency is around 25.76 microsecond achieved. In this figure, time required for different specs of the process is also we can see. In here, we can see for the MLP forward pass, take the most computational time for MLP hardware implementation. So that's how our hardware validation part ends. Now, key takeaways of the research area 1. What is that? How can we do the design for hardware software for structural health monitoring system? It starts with the data generation, then the co-design approaches, FFT and MLP, and we discuss about some experimental analysis with results. That's how the research area 1 ends. Now, for the overall dissertation, we can look at once again how this research area 1 add with the research area 2 and get my overall dissertation, where I already explained first half of this dissertation in my previous slides. Now let's start with the research area 2, adding physics. Along with the previously generated data, we also generated the single impact data here. The overall setup of this experiment is same as like the previous setup, but here is a new addition, which is a model hammer. We add here to make that sudden impact into the beam. So that's how we generate the single sudden impact. In the right side figure, we can see these single impact data in an overall process and zoom view or close view of that data. We generated several sets of this type of single impact data. Regarding PI data generation, I used a FEA model to make a steel cantilever beam to generate the PI data. As like real setup, here, this is a fixed support beam in excitation with the same experimental excitation force through the free end. And that's how FEA model uses all the physics variable itself to generate all the physics data at like the total displacement, equivalent elastic strain, X, Y, and Z axis displacement as well as. Here, for a single experimental data, we can see the left slide, the acceleration, the experimental data. Right side is the total physics informed data for this data. So what is the goal of this two figures? It can show the same type of trend we can see in the PI data as like the experimental data. It's mean FEA model can generate the realistic data for hydrodynamics or in case of any this uncertain data. Now come to the research question 2, adding physics direction 1, which is the data augmentation. Before it starts with the direction 1, let's see how the traditional model work. In case of traditional model, normally we feed a data as like experimental data or acceleration, and what is the output? It's also output the prediction over that acceleration or experimental data, a single input, single output. But as now we have the PI data along with experimental data, we use all of this data to build a problem-specific customized model to design a tailored model to address the specific hardware hydrodynamic system challenges. This model name is Physics Informed Series Prediction, in short, PISP. This model is kind of a physics data enhanced time series prediction, or we can say this model series prediction for PI augmented data. Now look at how this PISP is working. So in PIS, we send all of this data, experimental and PI. And in case of prediction, it's a single data over the experimental data or the acceleration. This is the simple overview, but let's look at inside how it's worked. So in this model, there are two phases, training and inference. In training, we can see inside how it's working. We feed experimental and FEA data, and data is split into batches and too many batches, and go to the model, measure the losses until we achieve the optimized value. Then we go the update parameter through the model, and batch by batch it's run, and finally we get the output from here in the training stage. But in the inference stage, we again use all of this data, experimental data and PI data. But in case of prediction, we just see the prediction over experimental data. In here is acceleration. To see the detailed PIS model, here is the flow diagram of PIS. So if we see the flow of this model, start from the below. If we consider the XA as experimental data acceleration and other of these, we consider the PI data. So there are several features along with PI and experimental data. The first, we use a bialystium to catch the series representation, and output of this is generate a latent feature to adjust the series length. Because the input and output length is not same, we use another fully connected layer to adjust the series. Next goal is to reduce the feature because we feed experimental and PI features. So there are several features like 4 to 5, but we need to only predict one feature. That's why we need to adjust series, go to the fully connected layer. And in the finally, we use the activation function to capture the nonlinearity of the data. And finally, we get the prediction over the acceleration value. Here is also happening the loss function calculation with the truth value to achieve a best performance from this model. And that is the experimental data acceleration over the prediction. So what is the PIS model? We already said it's a physics-informed series prediction. Why we use it for time series prediction? What type of physics approach we use? It's kind of enhance the accuracy of dynamics response for structural health monitoring. And we use here data augmentation like the univariate data, experimental data plus PI data. What are the components we use? With the bidirectional long short-term memory, bialystium, fully connected layer, activation function, CELU. That's all about the data augmentation approach. The result section is here. A total of 5 PI features we used here. The total displacement, strain, x-axis, y, and z-axis displacement. For analyzing the data augmentation approach piece, we set up 5 fashion of setup. First one, the 0 PI, where we have only the acceleration. In case of 1 PI, we add the one single PI, like the total displacement with acceleration. Then for 2 PI, there are 2 PI, total displacement and strain, and gradually 3 PI, 4 PI fashion. Now look at the results with different metrics. In case of RMSE, MAE, we can see when the physics-informed feature increase, error going down. Same pattern in case of MAE. In case of SNR, when we add more physics, we can see the results is perform better. It increase the SNR. It means there are less noise, more predicted signal. In case of trace, we follow when we add more physics, it's going closer to the value 1. It means it performs better. Now, from this plot, we can see a little bit the time series plot, how its performance looks like. From here, the red is the prediction, truth is the blue, and green are the absolute error. Here, the dotted line considered a non-stationary event. But for this plot, it's really not too easy to see the gradual changes of prediction over truth value because it's very tiny. But in the right side from the numerical numbers, we can see when we add more feature, more physics info feature, it increased the performance. This matrix I already explained, but the more important part here, how much percent improvement happened here in case of all of these metrics. So from here we can see compare with the 0 PI feature, we can see for RMSE, when there is 4 PI feature, the performance is too much. Like it's around 17.5% improvement. Compared to one feature, it's around like 6.6%. This type of improvement also happened in all other metrics when we increase more physics informed feature. As we test the model with a single data in our previous discussion and see the efficiency, but it could be a random effect or only for that data. So ensure the robustness of this PISP model and confirm that the observed improvements are not limited to a single data set. I tried also some other data to verify the PISP model efficiency. So in the first data is the same data I discussed in our previous slide, but along with this, I also made 8 more data. Here are all the data configuration. Mostly we consider the without physics, what is the performance, and with physics, I use the maximum PI, 4 PI, and look at the performance metrics change here. But it's hard to see detail in the table. So let's look at the plots, how these changes happen. For comparison bar plot, the below plot is showing the performance improvement, the upper plot showing the without and with PI, how the numerical value changes. So in the top figure, we can see for all of these metrics, the blue considered without PI, there is no PI. So in this case, we can see this blue line is up for both cases in the RMSE or MA, even for all of these 9 data sets. It's mean the error is high when there is no PI feature, but the green is the with PI, which is showing the low error for all this data. It means it's following the same trend as like the data 1 for all of these metrics. In case of SNR, we can see without physics has the lowest SNR for all of this data, but with PI, it has highest SNR as well as in case of track. In case of improvement, we can see for all of this data, here are improvement when we add PI. But the improvement is not same like for all of this data. It's sometimes lower, sometimes high. So there could be some reasons. That's why I put these 2 figures here, like hammering around time, like when we start hammering over each data and the hammering force. So from this figure, we can see from each data, the hammering time is varying and also hammering force is different, like 300, 400 or around that. So that could be the reason because each data are independent and unique from each other. That could be the reason of this variation in the performance analysis. Now, key takeaways of this approach, data augmentation. What are the pros? It can utilize the physics data. Yes. It achieves the better performance. Yes. So we can see the PISP model here. We use all the data, run to the PISP, training and inference, and do the prediction over the acceleration data. But still, there are some cons. We need still the physics data in the inference stage. But we want to solve this problem. So the solution could be transfer learning based model. So this slide actually giving us an overview, like though we already make a model, data augmentation physics informed model, why we need to make another model. So the key difference between these 2 models is here. The data augmentation model, what I just explained, here is the training phase where we feed experimental data and PI data all together in the training phase and do the experimental data in the output. In case of transfer learning approach, what we will talk in the upcoming slides, here I also used experimental and PI data in the training phase too. But in case of inference, in case of the data augmentation model, we need to use both of these data, both of these type of data in the inference, just doing a univariate prediction, but we don't need to use all of this PI data in transfer learning based model in the inference stage. We just need to feed the experimental data and to make the prediction over the experimental data. So that is the point. we make another approach, transfer learning, and which solves the cons of the data augmentation problem. Now we don't need to make a heavy weighted model for the inference stage. So now start with the approach to transfer learning. In here, we see at first the data augmented model, the piece in the top, which is the physics informed series prediction. So solve in case of piece model, we use all of this data through the training, also in the inference, and do the prediction. Now we introduce a transfer learning based model, what we named like physics informed machine learning for non-stationary temporal forecasting, in short, Pimento. So the below one is the Pimento or the transfer learning based model. We can see here is a training phase where we use all of this data, but in inference only use the acceleration data. We will talk detail in the upcoming slides. So here is a very basic concept of the motivation of this transfer learning model. How it's work. It's again start with the data generation. I think we explained that how we make the experimental data and physics data for FEM model. But main concern here, the basic model, how we made here. So this is kind of inspired by the teacher-student model phenomena. So here are a heavily weighted model, teacher model, where we feed all the data, experimental and physics informed data, and do the prediction from this teacher model. So from the teacher model, what we predict, we measure the loss with the truth value and do the propagation until we achieve the best performance. Then the training is done for teacher model. It's done. Then here is a student model, which is a lightly weight model, where we don't need to use any type of physics data, only we use acceleration data. And then we have the prediction. But this prediction, we make the loss measurement not with the truth value, but we make the loss function compare with the output of this teacher model and do the back propagation. And that's how make the student model give the most best performance. That's how this information from the teacher, it's transferred to the student model. That's how it's make the transfer learning approaches here. So this transfer learning, we can see the detailed flowchart of this Pimento model, the training phase. Here are two models. We consider the corrector model, which is as like the teacher model, which is the assistive model. Here is it's like a encoder and decoder based model. The simple model, the student-like model is the estimator model here. In case of corrector, we send all the features. In estimator, only one features in training phase. In case of inference, only we have the estimator model. And here is the input of the acceleration and output is also the acceleration over the forecasting. In the below 2 point, giving us a simple scenario, how the corrector model input and what is the estimator model input. So corrector model, which is like the teacher model, we feed all the data, acceleration, all the PI data, and get the output. In estimator, we just need the experimental data, no need of physics data. Here are more detailed layout of this model, but I don't want to make people bored to explain all the mathematical terms. But just a single thing we can see, the blue is considered like the corrector model, where we send all of this data as a vector representation. Then here is the encoder and the decoder and the final output. But in case of estimator, we just feed one single data. Here is the encoder and decoder itself, but this decoder is as similar as like the corrector model. This is the same decoder shared. So that's how it's shared the transfer learning knowledge through the decoder too. So that's how its two model works together in the transfer learning model Pimento. Now look at the results. We make model. It makes no sense if we don't have results and see the better performance in the model. Same type of feature we use here, but with the different data, like the total displacement, strain, X, Y, and Z axis displacement. Also, in case of transfer learning setup, we use 5 fashion of data, 0 PI, where we only have the acceleration, no PI feature. For 1 PI, we add a string. For 2 PI, we add Y, Z axis displacement. And for other fashion, 3, 4, we add more PI. Now look at the performance for the different matrix. In RMSE, we can see when we increase more feature, it decreases the error. Same thing happen in case of MAE, decrease more PI, have less error. In case of SNR, it's going up when we add more feature. Also in case of track, adding more feature means good performance. Again, not only stop with the matrix, we can look at the time series plot. Here we can see the red is the forecast, blue is the truth, and blue here is the absolute error in the green. Non-stationary event is here, the black dotted line. So from all of this prediction, when the sudden impact happened, we can see here is a high chunk of the error. Then after for a certain time, it's going down. But it's really hard to see the close view of the changes from this time series plot. But for the numerical values, we can see in the right side, it performs better. And also in this plot, we already explained how it's worked. So now look at how much performance improved after this addition of physics PI features in this Pimento model. Yes, it's improved a lot. When we add more physics around like 4 PI, it's more than 35% improvement happened. Also, it's happened for all the metrics. So one of the important point here, all of these results, it's from the estimator, which is actually our main model where we don't need to use any type of PI model, which is a light-weighted model, and that is the output result. All of these results from the estimator model. Now, from result analysis, we can look at the corrector and estimator performance also, though our main model is the estimator, but we can see in this plot for the corrector and estimator, corrector, which is acts like the assistive model, in estimator, which is a lightweight model. In both of this case, we can see when we increase the physics informed feature, it performs well. But the main thing what we need to notice, in case of estimator, it performs even better compared to the corrector. But why? It's better due to the less overfitting and gaining more generability. So we can see this performance better for estimator in all of these metrics. For this analysis, I used input window 10,000 and output 500, but it doesn't come out from nowhere, not like that. We need to make so many sensitivity analysis to reach this input window and output window. So effects of the input dimension for this plot, the right side, we can see when we consider outside window 500 and we make that ranges between input dimension 0 to 30,000 to check which performance is better. We use a second order fit so we can see what is the trend we can see here with each matrix. So from this analysis, we find out the 10,000 input window is better for corrector and estimator too. To find the effect of the output dimension in this below figure, we consider the input window 10,000 constant and do the analysis for the output dimensions is range around 0 to 10,000 and we do more. But here we make the zoom part where we see the most changes. And from here, we can see the final or the best performance we achieved from the input window 10,000. So that's how the overall sensitivity analysis is done for the transfer learning based physics informed model Pimento. And here again come to the overall dissertation, how it's all together works and make how to design, how to add physics, and finally both of these make the final dissertation hardware software design for temporal forecasting in structural health monitoring. Conclusions. The summary of this overall research is in the research area 1. We do the answer for how to design hardware software for structural health monitoring. We did experimental data generation, show the co-design approaches for hardware and software for FFT and MLP, do the analysis of the result in research area 2. we did give the answer how to synergize between data-driven and rule-based system, do the experimental data generation, also physics data generation. Two approaches, first one, the data augmentation-based model, then the transfer learning-based model. And here is the glimpse of the research question one, how we combine that hardware software design. In case of A50, MLP software and hardware design we made. The second glance for the research question two, how we add physics, how we made two approaches, that augmentation approach and the transfer learning based approach. And finally, we combined these two for my final dissertation. Now again, come back to the key contribution, what we already talked previously, but little bit overview. It helps for data generation, also for data-driven model development, physics-informed model development, hardware implementation, application in higher dynamic system. Beyond this, also there is another project work, the Levy Bridge assessment. Now, once again, come to the publication slides. We discussed detail, but we can see once again in the summary, I have the 10 published paper, one submitted paper, 3 submission stage paper, and 1 future plan, which is in the development stage paper. Now, this is the most favorite slide of the overall presentation, which is the acknowledgement. First, I want to thank Arts Lab. I feel fortunate to have been part of a lab filled with kind and cooperative colleagues, and their friendship and support have made this journey more rewarding. I also want to deeply thankful to Dr. Beckers, Dr. Wang, Dr. Lee, and Dr. Jasim. Their encouragement, time, expertise have made a significant impact on my learning and research. I also appreciate the help and support of all the collaborators, course instructor, school staff, relatives, and friends. Finally, I would like to thank NSF and Air Force Office of Science Research for funding this work and the other project I accomplished during my PhD program. A big thanks or a special thanks to my advisor and mentor, Dr. Austin Downey. He is a person with his exceptional patience, guidance, and support taught me not only research, but also instilled in me a profound sense of professionalism and growth in personal life. A big thanks to my family, including parents, life partner, who always support me mentally and physically through my overall PhD journey, my siblings and in-laws. Also, a new addition in my life, my newborn, Upakhanoiki Chowdhury, for bringing me joy and tranquility throughout my pregnancy and beyond. I want to give a heartfelt, immense love to my baby. Finally, gratitude to the divine power that ensures everything works perfectly, always. I really want to thank all of you. And next, thank you for attending my presentation. Any questions and comments?